In this episode of our British Science Week Coffee with a PhD Student podcasts, Annabella will be interviewing Tymoteusz Miara to find out how we can solve the mysteries of fluids.
Hello, welcome back to the AMPO British Science Week podcast. I'm Annabella and I'm here today with Tim.
Hello, I'm Tim. My real name is longer than that, is Tymoteusz, because I'm from Poland originally. But I've been here in Manchester for 6 years, more than 6 years now. I did my undergrad with masters for 4 years, and now I am in my final year of my PhD.
Fun. And what area of physics do you work in?
So I work in fluid mechanics. And I know that if there are any engineers listening to this, they're probably thinking I'm a masochist. Usually fluid mechanics is considered to be one of the more difficult courses in their syllabus. But yeah, I enjoy it.
That's good. What do you enjoy about it?
So I think first, there are, I think, several things I enjoy it. I enjoy the fact that it's roughly the size of everyday life stuff. So it's not something astronomically big that we can't touch or can't reach. And it's not something astronomically or microscopically small that you can't even see. Yeah, it's working with real stuff that is involves a lot of experimentation, working with hands, producing certain objects, and I really like working manual work as well as scientific work. So
yeah, so you're an experimentalist, right?
Yes, I am.
Amazing.
The second thing I enjoy about it is that it is actually, maybe it will sound strange, but I like the fact that it's in principle unsolvable. The equations of fluid mechanics do not have a mathematical solution, a closed form solution as they call it. So what we are doing is actually trying to figure out explanations that provide insight into what is happening, even though we cannot put an exact equation. We can still approximate equations, so we can try solve them with simulations, but the point is that even when you produce simulations, and even if you have a simulation that can predict what's going to happen, you still need this insight to provide this insight of what is actually happening in the system. So yeah, it's I think I like that. It's a bit of a detective work. Mm-hmm. You're trying to figure out what's going on, and even if you have a computer model that were to perfectly predict, it would not be as insightful as actually doing the science and trying to understand why things are the way they are.
Yeah, so there's a lot of reliance on experimental work as well.
There
and not just computational modeling and mathematical stuff.
Yeah, that's right. So fluid mechanics has those 3 branches. Most of it is experiment, simulation, or theory. The theory is always approximate. Simulation tries to approximate numerically by just, with computers, try and get closer and closer to the real solution. And experiment has its own challenges as well, but that one is usually ideally we would be able to compare all 3. Sometimes theory is not available, then we try to compare experiment versus numerical simulation. But ultimately we strive for each study, whether it's numerical or experimental, to stand alone on its own. So we should be able to understand what's going on, even if we just look at the experiments or just look at simulation.
That's really interesting. So what specifically have you been looking at during your PhD? What topic have you been focusing on?
Yeah, so this is a topic that I've worked for far longer than just my PhD. I did a few of my summer projects in Manchester here on this. So I'm looking at, well, maybe to picture it first, imagine you have a leaf falling off a tree, and it falls usually in this either tumbling motion or very chaotically, or sometimes maybe it will be just oscillating, kind of going left, right, and as it falls.
Just sort of floating down gently.
Yeah. And of course it depends on the shape. And essentially what I'm studying is not like this, but what I'm studying is a flexible sheet, or a rigid sheet as well, falling in a very viscous liquid, very thick. So imagine a maple syrup like very thick liquid. It doesn't actually matter what the liquid is or even what the sheet is. What matters is how thick the liquid is. So what is its chemistry is not as important as its physical properties. It needs to be very, very thick, because otherwise, if it's like air, there are turbulence, and that's a way different branch of fluid mechanics.
Yeah.
So what I'm looking at is no inertia regime where viscous forces dominate the whole thing.
Okay, and what are the like practical applications of that? Like, why, apart from just pure scientific curiosity, would we care about this?
Right, so I think in particular the flexible sheets are of interest because recently you might have heard of graphene. Within the last 20 years we've discovered graphene, and we are storing actually graphene flakes in viscous environment, in liquid environment. And the graphene flakes are very small. They are, I think, the largest that I've seen. My knowledge is not maybe particularly up to date, but they are, I think, 0.5 millimeter are one of the kind of record large sheets, but they're incredibly thin. They're 1 atom thick, and they that means that they are also very flexible, very, very floppy. If we store them in a liquid environment, they will as they fall, because they are heavier than water, as they fall, they would bend. So as they sediment downwards, they interact with the surrounding fluid in a way that causes them to bend, possibly wrinkle. So I'm looking at this fluid structure, this flexible structure, which is the sheet and the fluid, this interaction between them. Because as much as we store and process, and we sometimes segregate graphene flakes by their sizes, by looking at how fast they fall, we don't actually know how fast they do fall, because they change their shape. Depending on their size, they also change their shape differently. So that affects also the speed at which they are falling. So I'm hoping that we will be, at least on a fluid dynamics perspective, we will be able to catch up with the current state of how graphene is processed. We'll understand. So at the moment, I'm only studying a single sheet in an approximately infinite fluid. So it's a tank that is much larger than the sheet that I'm studying. Just one thing on its own. But hopefully, that will, I'm hoping maybe this year, I will look into suspension, so multiple sheets or hundreds of sheets in a tank, and see what then happens. Yeah, so I think these are kind of applications, potential applications. It's also a part of more of a just everyday life. Like we know, well, or roughly, people have studied how coins, for example, fall through water. Whether they can fall sometimes chaotically, sometimes they tumble, sometimes they fall gently down. So it's all part of a bigger picture of various everyday life phenomena. And if you want to see tumbling motion, you can just cut out of a paper just a narrow strip, ribbon, a bit like a confetti. You drop it in the air and you will see how it just spins and tumbles through as it falls. It's quite an interesting thing to play with, actually. So it's all kind of connected here.
That's fun. Yeah, so you've got a lot of like actual connections to things you can do in real life, which personally that's also something I really enjoy about physics. So moving a little bit away from actual research, what made you decide to actually pursue a PhD after you were done with your undergrad? Like, why did you decide to do that and not just, go off and get a job?
I wanted to do a PhD even before I came to university. I knew that I want to. I'm just curious about how the world works. There is something that I just want to know a bit deeper than what I would sometimes even read in the internet. Although there is a lot of excellent stuff now in the internet, which wasn't there when I was a teenager. But yeah, I wanted to. I have this kind of deep thinking mind that I want to go in depth and understand something in depth. So yeah, that's I wanted to do research before even I came to uni. I like the fact also, I think particularly this research rather than something else is that it is, I used to have as a kid even passion for electronics. I did all sorts of, I had a phase of being passionate about geology, but it was all kind of hands-on experience. So I think this fluid mechanics fits perfectly with it being something that I also, work with my hands. I operate a scalpel sometimes. It was something I've done already since I was 7 years old. I think I'm at a good spot at the moment. I really like what I'm doing.
I mean, that sounds amazing. Being able to do something you're passionate about and finding a niche in it that you fit into sounds pretty amazing.
Yeah, I think the thing is, I mean, often people ask me why have I not chosen those much more cutting edge fields. Like fluid mechanics is not. It does not attract as much attention as astrophysics or particle physics, studying fundamental reality. But I think that there are when you choose your career, you've got to also factor in your personal personality. Yeah, your preferences into, do you like to work with your hands or program code a simulator, or what you want to do.
I mean, if everyone did the same research, it would be boring. So, what is it actually like being a PhD student? Like, what do you do on a, let's say, like a weekly basis, approximately? Like, obviously not like, day-to-day schedule, but like, what are the kind of things that are expected from you that you do?
Right, so I work, I think, well, at the moment, now that I've done a lot of my preparations, but most of my first year was building and proving that it works, the experimental setup. So methods of actually performing experiments. And it took me longer than I wanted it to, but it took me essentially 2 years to make sure that everything is working. But now that I have that, I'm able to drop sheets and reconstruct their three-dimensional shape as it evolves in time, as it falls through the fluid. Now my work is, half of it is in the lab doing experiments, and the other half is reconstructing and doing analysis on those experiments. So there was, and there still is, a lot of coding because the data is recorded, the experiment is recorded on a camera, and I have to reconstruct, process the videos, and extract the real data in space. But then there is also there are various technical challenges as well of producing accurate sheets, whether they're flexible or rigid, and of particular shape that we want. So it's a lot of experimentation. It's a lot of coding. It's a lot of just trying to understand what on earth is going on, because we've come to certain very counterintuitive results as well that actually took more than a few hours of discussing with my supervisors of what's actually going on there. So even though it's a simple problem, it proved to be much more interesting and complicated than we thought. So,
final quick question. Thinking back to yourself pre-university, so still in school, what's like one piece of advice you would give someone in that kind of situation? Like something that you might not have heard at the time, or you wish you would have heard? Just Or maybe a piece of advice that you found very useful.
Well, I think I found what I found useful from other PhD students or in general. I found the advice is that you really need to know that you want to do an in-depth research. It will be boring. As much as I like going in a lot of depth, there have been literally just months where I did the same thing over and over again, and anyone with whom I was talking about it outside of physics, they were like, how can you devote all that focus and so much work on something that doesn't even work for months? So you've got to be patient.
Yeah.
It is. If you're not a patient person by nature, you will have to think 10 times before committing to something like that. But on the other hand, if you are motivated by understanding and by curiosity, and you want to understand, you want to also have independence, because there is a lot of independence of what you go into. You actually, you're not doing what you're told, you're actually doing what you find is most interesting. So there is a bit of, there is a large element of discovery. The supervisors are not micromanaging you. You are given a lot of freedom in choosing how you want to tackle the problem. These are also unstructured day. You can work. You don't have to show up every day to the lab at a particular hour. You can choose how you your schedule. You can choose when you do things. So there are many good rewards that they actually they happen to fit my my personality. So that's why I enjoy it. But yeah, you've got to be sure you want to do it. Bear in mind, it is 3.5 years here in Manchester. It's not like it's not the whole life.
Yeah.
It's the problems are usually complicated enough that you are not getting completely bored. It's not like you will solve it within 1 year and that's it. No,
yeah.
there is stuff to do. But you've got to make a decision. Do you want to spend on something your 3.5 years of your life?
Fair enough. Well, very nice to talk to you. Very interesting research. And yeah, that was it for this episode. That's it. Bye-bye.
Bye.